Hey guys, welcome to this Mometrics video on the scientific method. Before we dive into the what, let's first talk about the why. Why do we need the scientific method? Well, there are numerous reasons why there should be a method behind anything that we do. There needs to be consistency, there needs to be a logical flow, there ought to be consensus, and the experiment must be able to be replicated. If everyone were to just do their own thing, then there would inevitably be fabricated scientific research posing as facts, lacking in consistency. The first step in the scientific method is to make an observation. All scientific investigations start because someone observed something that happened and it stirred up in them a curiosity. For example, Isaac Newton observed and experienced an apple falling from its tree. It actually hit him on the head, at least as the story goes. This observation eventually led him to ask questions, which leads us to the next step in the scientific process. Ask a question. Questions help us to hone in on the information that is actually worth investigating. A question Isaac Newton probably asked might have been, why do things always fall to the ground and not go up? Naturally, questions beg for an answer, and this takes us to our third step. Propose an answer by developing a hypothesis. Generally, a hypothesis is defined as predicting an answer based on things that you already know, or an educated guess. With our apple falling from a tree problem, Isaac Newton probably had some experience that allowed for him to formulate a hypothesis. Perhaps he had thrown a ball before and picked up on the fact that the ball generally goes in the direction that it's thrown due to the direction of the force. So, when it comes to formulating a hypothesis, you start with what you know. When working to formulate your hypothesis, you ought to use deductive reasoning. This generally takes the form of an if-then statement where you move from a general truth to a specific. Something that is crucial and must be noticed about an if-then statement is that 1, it is testable, and 2, it is refutable. Your hypothesis must contain these two qualities or else it does not follow the scientific method. The fourth step in the scientific method is to conduct an experiment. This is the step where you test your hypothesis. When testing your hypothesis, the experiment must be controlled. You must control every single variable so that you are able to study a single variable. This is where the terms dependent and independent variables come into play. The independent variables are the variables that are controlled by the researcher or experimenter. The dependent variable is the variable that is left untouched by the experimenter and is observed and measured for any change. The other thing that is crucial when controlling the experiment is having a control group and an experimental group. This allows for the researcher to be sure that his results are consistent and not based on chance. The fifth and last step in the scientific method is to observe your data and draw a conclusion. When analyzing the data, you will have collected qualitative and quantitative data. Qualitative data is data that represents information about qualities. For example, the color of a liquid, the smell of a substance, or maybe the softness of skin. These are all examples of qualitative data. Quantitative data, on the other hand, is data that can be measured numerically. For example, the amount of lashes on your eyelid, the height of a tree, or perhaps the time it takes for you to run a mile. These are all examples of quantitative data, or data that can be quantified. As you analyze your data, you have to decide if the data you collected proves or disproves your hypothesis. This is where you draw your conclusion. The conclusion of your experimentation should answer your original question.
Hi, and welcome to this video about molecules. Before we get to molecules, we need to start with atoms. Atoms are the smallest unit of an element that still maintain the chemical properties of the element. This means that while atoms are made of smaller pieces, protons, neutrons, and electrons, it is the specific combination of those pieces that defines the element. Atoms interact with other atoms to give, take, or share electrons in order to fill their valence shell. When atoms share electrons, they form covalent bonds. The resulting collection of bonded atoms is what we call a molecule. Just like an atom is the smallest unit of an element, a molecule is the smallest unit of a covalent compound. We'll discuss ionic compounds later and consider why these are separate from molecules. Because most covalent bonds are formed between nonmetal elements, molecules are typically made of nonmetals, shown here on the periodic table in yellow. Noble gases are an exception here because they already have a filled valence shell and don't form bonds under standard conditions. Nonmetal elements, with the exception of the noble gases, naturally exist as molecules rather than atoms. For instance, you would rarely encounter an isolated hydrogen atom. Instead, we find hydrogen as a two-atom or diatomic molecule, H2. Each hydrogen donates its electron to form the covalent bond in H2, thus filling the valence shell of each atom. This lowers the energy of the system and is more stable than two isolated hydrogen atoms. Here, we have highlighted the elements that exist as molecules. As we so rarely encounter these elements as single atoms under normal conditions, it's common to refer to the molecular form by the element name. This means that we must use the term atomic when we want to talk about the individual atoms of these elements. For example, if we said that chlorine gas was emitted from the reaction vessel, we would be saying that molecules of Cl2 were being released, not chlorine atoms. The types of molecules that we've been talking about here are known as homonuclear molecules, molecules made up of atoms of only one element. Of course, atoms of different elements can combine to form heteronuclear molecules, which allows for an infinite number of combinations and creates chemical diversity in our world. Molecules range from small diatomics like carbon monoxide to large complex structures like proteins and DNA, which can contain hundreds of thousands to billions of atoms. While molecules come in all shapes and sizes, the important thing to remember is that the molecule is the smallest discrete unit of the compound. Let's look at a cup of water as an example. If we could shrink down to the atomic level, we'd see H2O molecules dynamically interacting with each other. Even though the molecules are attracted to each other through intermolecular interactions, the bonds between the atoms within a molecule are many times stronger since they share electrons. So we can still identify individual molecules. Here, we've circled the individual molecules in green. The same is true when we consider larger molecules like oleic acid, one of the primary fatty acids in olive oil. Again, if we could shrink down, we'd see an array of molecules interacting with each other but maintaining their individual units. This is an excellent place to stop and think about why we don't consider ionic compounds molecules. Ionic compounds are typically between a metal and nonmetal atom where the metal gives an electron to the nonmetal. Once the electron is given away, it is no longer connected to the atom it came from. Each atom has a full valence shell. As an example, we have sodium donating an electron to chlorine to form an ion pair between a positive ion, called a cation, and a negative ion, called an anion. When in solid form, the ions are held together by a strong electrostatic interaction between a positive and a negative charge, called an ionic bond. While it is easy to imagine this happening with just two atoms as a solid, the pairs of ions are arranged in a repeating and continuous crystalline structure. In this form, each sodium ion is surrounded by chlorine ions and is attracted to each equally, and there is no longer any clear distinction of individual pairs. This is one of the reasons we do not consider ionic compounds molecules. Another way that ionic compounds are distinguished from covalent compounds is by comparing the electronegativities of the elements bonding. Electronegativity is a measure of an element's attraction to electrons. In general, this property increases as you go right on the periodic table and decreases as you go down. Ionic bonds are classified as those with a difference of electronegativities greater than 2. Before we move on, let's take a second to discuss a different ionic compound, one with a polyatomic cation, sodium acetate. Let's specifically consider if sodium acetate were dissolved in water and acetate were floating in solution. Would that be considered a molecule? While your first instinct might be yes, after all, it is a group of covalently bonded atoms, this technically is not considered to be a molecule because it carries a charge and therefore wouldn't be found in bulk on its own, like water or oleic acid. So, by the strict definition, molecules are always neutral. That being said, chemists and biochemists often use a more relaxed definition and may refer to a charged group of covalently bonded atoms, like acetate, as a molecule. Now that we have a grasp on what molecules are, let's consider when they form. New molecules form as a result of a chemical reaction. The covalent bonds of the molecules break, and the atoms reorganize and connect to form new combinations of atoms and thus new molecules. As an example, nitrogen, N2 in red, and hydrogen, H2 in blue, recombine to form molecules of ammonia, NH3. This is a chemical change. Though made of the same atoms, ammonia molecules have entirely different properties from both hydrogen and nitrogen. This is in contrast to when covalent compounds undergo physical changes, like a phase change from liquid to gas. In that case, the molecular unit stays intact, but the intermolecular interactions change, here shown with water converting from liquid to gas. Every molecule is still a unit of H2O, but they are now interacting much less in the gas phase. Let's wrap up with a review of what we've covered today. Molecules are collections of covalently bonded atoms. They are the smallest unit in a covalent compound and determine the properties of the bulk substance. Ionic compounds do not have distinct molecular units, and they are not considered molecules. Charged covalently bonded polyatomic substances are also not considered molecules by strict definition. However, many chemists relax the definition when it comes to these compounds. Molecules are formed during a chemical reaction when bonds are broken and reformed between atoms. This is in contrast to when a covalent compound undergoes a physical change, in which the molecular unit stays the same, but the interactions between molecules change. Finally, let's finish with a quick test of our knowledge. Which of these substances is a molecule? Helium or oxygen? The answer is oxygen. Helium is not a molecule because it is a noble gas and exists as an isolated atom. Oxygen is a molecule because it is one of the non-metal elements that is found naturally as a diatomic, O2.
Hey guys, welcome to this Thermometrics video over chemical reactions. In this video, we'll take a look at the definition of a chemical reaction, characteristics of chemical reactions, types of chemical reactions, and other things that are pretty important to know. First, the definition. A chemical reaction has taken place when a chemical substance alters its initial chemical identity and takes on a new chemical identity. So basically, what's happening is you have at least two molecules that come together perfectly, hitting each other in the exact right way, and these two molecules, change into something else. That's typically how all types of reactions work. For example, you have an eager and excited teacher who says, "Science is very important. You need to learn. So do your homework, do your homework, do your homework." Then let's add to the equation that one guy in the class who says, "I didn't do my homework." When these two come together and react, the product will be a very unhappy teacher and a slightly terrified young boy. In this example, we can see some observable differences after the reaction has occurred. Well, the same thing is true with chemical reactions. Every chemical reaction yields a different result, which inevitably means that chemical reactions will not all have identical observable properties. However, if you mix two chemicals together and want to know if they reacted with one another, you could look for these observable characteristics. Irregular change in color. If you mix white and red together and get pink or light red, then that's probably not a sign of a chemical reaction. That's just what happens when you mix the colors red and white together. However, if you mix a red and white substance together and get blue, then you might have a chemical reaction. Change in consistency. When two substances are mixed together and there's a change in consistency, then this may reflect a change in the molecular structure. So if you take two runny liquids and mix them together and the product is a thick jelly substance, then you might have a chemical reaction. Change in luster. Luster refers to the reflective quality of a substance. So if you mix two dull, murky substances together and they produce a really glossy or polished substance, then you might have a chemical reaction. Appearance of bubbles or froth. The formation of froth or bubbles may suggest that a gas has been composed in the chemical reaction. Change in odor. Now, if it's just a slight change in odor, it's probably not a chemical reaction. So if I mix a substance that smells like honey, now this is just a silly example, with a substance that smells like vanilla and the ending result smells like some type of syrup, then it's more than likely not a chemical reaction. If you take those two same substances and mix them together and their product smells like a smelly sock, then you may have a chemical reaction. Change in temperature. You can use the thermometer to take the temperature of each substance before, and if there's a change after the two have been combined, then there may be a chemical reaction. Precipitate formation. This just means that an insoluble solid is formed from a liquid solution. If this happens, then you probably are witnessing a chemical reaction. So those are some observable characteristics that may signify that a chemical reaction has taken place. Now let's take a look at 5 different types of chemical reactions. Number 1, combination reaction or synthesis reaction. A combination reaction is pretty straightforward. It can be defined as when substances are mixed together and they form a new compound. Here's what the combination reaction equation looks like. A plus B yields AB. As you can see, these two substances literally combine to form a new substance. An example of this is carbon solid and oxygen gas reacting together to form carbon dioxide gas. Number 2, single replacement reaction. A single replacement reaction, also known as displacement reaction, can be defined as a chemical reaction in which one element displaces or replaces, whichever word you would like to use, a comparable element in the compound, causing a chemical change in the compound. Here's what that looks like in equation form. A and B plus C yield AC plus B. As you can see in this equation, C has stepped in and replaced or displaced B. An example of this is the combination of copper and silver nitrate. 3, double replacement reaction. A double replacement reaction can be defined as a chemical reaction in which the ions of two compounds swap with one another within a liquid solution and configure two new compounds. Here's what that looks like in equation form. An example of this is the combination of sodium sulfide and hydrogen chloride to produce sodium chloride and hydrogen sulfide. Sodium and hydrogen are cations, and sulfur and chlorine are anions. The cations and anions switch places during the reaction to form new compounds. Number 4, decomposition reaction. Decomposition and composition are opposites. In a decomposition reaction, a single complex compound is broken down, or decomposed, into a more basic substance. Here's what that looks like as an equation. A, B yield A plus B. Now, there are actually 3 different subtypes of decomposition reactions: thermal decomposition, photodecomposition, and electrolytic decomposition. The term that precedes the word decomposition refers to the type of energy used to make the decomposition possible. So, in thermal decomposition, heat is added to the complex compound to decompose it. In photodecomposition, photons, or light, is added to the complex compound to decompose it. And in electrolytic decomposition, electric current passes through a liquid solution to decompose it. For example, the electrolysis of water. Water decomposes into hydrogen and oxygen when an electric current is added. Number 5, combustion reaction. A combustion reaction can be defined as a chemical reaction where a substance mixes with oxygen and produces substantial amounts of energy that take place in the form of heat and light. An example of this would be the combining of methane and oxygen to produce carbon dioxide and water. Now, the last thing we'll talk about, as promised, is other things that are pretty useful to know. There's a lot that I could go into here, but I just want to talk about 2 things. The first is basic language, and the second is reaction rates. Basic language. You should already know this, but here it is. The individual substances, before they are combined together to react, are called reactants or reagents. These reactants, once combined, yield a product or products. Secondly, reaction rates. Now, there's a lot that goes into this, but I'll give you the most basic idea of what this means. Chemical reactions are all over the place when it comes to speed or rate it takes for the reaction to occur. Some reactions happen instantaneously, and others take years and years. Well, reaction rates are dependent upon certain characteristics of the reactants. There are two variables in which the reaction rate is dependent on: the change in concentration of a substance and the time it takes for the change to be observed. Well, this rate of change can be altered via a catalyst, which speeds up the chemical reactions, or an inhibitor, which slows down chemical reactions. Understanding how chemical reactions work is important, but understanding the rate at which they take place is equally as important. Hey everyone, welcome to this Mometrics video over the 4 laws of thermodynamics. Thermodynamics is a branch of physical science, or physics, that focuses on the correlation of heat and all other forms of energy, and consequently, all forms of energy that relate to one another. Well, the 4 laws of thermodynamics work to define the foundational physical quantities that mark thermodynamic processes when at thermal equilibrium. These foundational physical quantities include temperature, energy, and entropy. Now, let's take a look at how these laws are defined. The 0th law actually came after the first 3 laws of thermodynamics, but it was actually so fundamental and provided a basis for the other laws that it got the name 0th. That way, people knew the order in which they should learn or think through the other laws. So, what does the 0th law actually state? Let's take a look. Let's say that you have 2 systems, A and B, that are connected to each other with some sort of barrier between them. Well, the heat or energy of A will transfer over to B, or vice versa. The energy of B will transfer over to A. This is assuming that the wall is diathermic, meaning that heat can be exchanged, as opposed to an adiabatic wall, which would not allow for heat to pass. Once heat or energy is transferred between 2 systems such that there is no more heat being transferred or the transference of heat stops, then the systems have reached equilibrium, more specifically thermal equilibrium, since we are talking about heat. Now, let's say that we have another system, A and C, and they also reach equilibrium. Well, since A is in equilibrium with B and A is in equilibrium with C, then when you take B and C and place them together with a diathermic wall, then there will be no transference of heat. This is because the 2 systems are already at equilibrium together. To say this mathematically, you could say if A equals B and A equals C, then B is equal to C. That's the 0th law of thermodynamics. For some of you, this may seem like common sense. To others, it may seem counterintuitive, especially if you are super familiar with Boyle's law. Regardless, this is what the 0th law shows us, but it gives us much more than that. The illustration you just saw tells us something. What is that? What is that physical quantity which determines that the 2 systems will reach equilibrium and the transference of heat will stop from one system to the other? Well, it's this very physical quantity that was discovered later. There were already 2 laws of thermodynamics in place, the 1st law and the 2nd law. Well, in these 2 laws, the term temperature was used, which was thought of as this degree of hotness, basically. While the term temperature was being used in the 1st and 2nd law, no one could actually define it. There wasn't really a way to define temperature within thermodynamics. So, the 0th law was made so that temperature could be defined. So, how is temperature defined? Here we go. If there are 2 systems in contact with each other, then the direction of heat flow tells us that one body is at a higher temperature and the receiving body is at a lower temperature. So, temperature is the physical quantity which determines the flow or direction of heat. So, temperature decides if heat will flow from A to B or from B to A. Let's review that real quick. First, 0th law says that if 2 systems, C and B, are in thermal equilibrium separately with a system A, then C and B are also in thermal equilibrium with each other. Secondly, the physical quantity defined in the 0th law is temperature. And lastly, Temperature can be defined as the physical quantity which determines the direction of flow of heat and is the one that is equal in a state of equilibrium of two systems. That was the 0th law of thermodynamics. Now let's take a look at the first law of thermodynamics. Here's what the first law of thermodynamics states. Heat energy given to a system is converted to its internal energy and work done on that system. To put this even simpler, the first law of thermodynamics just states that energy cannot be created or destroyed. It can only be transformed. Let's look at that mathematically. Internal energy represented by delta U is equal to heat energy plus work done. This equation is known as the first law of thermodynamics. But I'm guessing this still doesn't make sense to you. I don't blame you. Let's look at it this way. You have a system. Everything on the outside of that system is the surroundings. Well, energy can flow either into the system or out of the system. There are two ways in which energy can flow in and out of a system, which is through heat and work. So let's say that heat flows into the system. When heat flows into the system, then the system accumulates or gains energy. That energy is called the internal energy of the system, which is where we get our symbol U. The surroundings can do work on the system. So heat and work are the two ways in which a system can increase its internal energy. If the system's surroundings were to do 150 joules of work on the system, that means that the system's internal energy increases by 150 joules. And since the change is positive, delta U goes up. And since we know that energy cannot be created or destroyed, only transferred, the energy had to come from somewhere, the surroundings. So if the system's internal energy increases, then the energy of the surroundings must decrease. Well, energy follows this same principle. It cannot be created or destroyed. It's simply transformed or transferred from one place to another. The next law we will look at is the second law of thermodynamics. Now, the second law of thermodynamics might seem like an odd law. Why? Well, firstly, because the second law of thermodynamics doesn't tell us what can happen or what is possible. It only tells us what cannot be done or what is not possible. Another reason it might seem odd is because there are several ways to state it. The second law of thermodynamics states that the efficiency of a process can never be 1 or 100% of any machine. If a machine or process operated with 100% efficiency, then all of the heat or energy put into a system would be completely converted into work done, and there would be no heat rejected out. The second thing the second law of thermodynamics states is that unless you apply a pump into a system, there is no way to send heat from a cooler source to a source at a higher temperature. Another popular way to state this law, as put by Clausius, is no process is possible whose sole result is the transfer of heat from a colder object to a hotter object. Put very simply, the second law of thermodynamics tells us that heat will never flow from a colder object to a hotter object unless you use a pump to do so. Like how a pump is used to cool the inside of a refrigerator. In every other case, however, heat always goes from the object at a higher temperature to the object with the lower temperature. And the other thing it states is that within a system or machine, heat or energy will never be 100% converted into work done. So if I put 100 joules into a system and I get more than 100 joules out of the system, then one of three things has happened. 1, I lied. 2, I miscalculated either my input or my output. Or 3, I just turned all of physics and science on its head and defied all of it. The third law and last law of thermodynamics defines absolute zero and brings together the concepts of entropy and temperature from the latter laws. The third law states that the entropy of a perfect crystal approaches zero at a temperature of absolute zero. We can't actually achieve absolute zero experimentally, or at least you probably won't. This is because we know from the second law that heat is spontaneously moving from a warmer body to a cooler body. So the object that you are trying to get to absolute zero will be constantly taking in heat from its surroundings. I said that the lowest possible entropy will only occur in a perfect crystal. Well, a perfect crystal is a structure where all of the atoms are identical and are positioned in perfectly symmetrical ways. If there are any imperfections in the crystal, then that imperfection carries an energy with it, which does not allow for the minimization of entropy. Another important note is that if we can't get to perfect zero, then there will never be complete stillness in our universe because we will always have some sort of motion due to thermal energy. When someone tells you, get your head out of the clouds, you should tell them you can't help it because you live in the troposphere, and there are 4 additional layers of the Earth's atmosphere. Before we get into the layers of Earth's atmosphere, I want to share with you what it's made of. The atmosphere contains 78% nitrogen, 21% oxygen, about 1% argon, and 0.04% carbon dioxide, and then various small amounts of neon, helium, methane, krypton, hydrogen, and water vapor. As I vaguely mentioned, there are 5 layers to the Earth's atmosphere. In order from closest to the surface to the furthest from it is the troposphere, stratosphere, mesosphere, thermosphere, and the exosphere. The troposphere is the atmospheric layer closest to the surface of the Earth. It is 4 to 12 miles thick and contains about half of the entire atmosphere. As you've figured out by now, this is the layer of the atmosphere that sustains life. The parts of the troposphere closest to the ground are warmer, and the farther up in this layer, the colder it gets. Additionally, lots of water vapor and dust get trapped in this layer, which helps with the formation of clouds. The second layer, the stratosphere, starts above the troposphere and extends to about 31 miles above the Earth's surface. The stratosphere holds the ozone layer and absorbs the harmful radiations from the sun. The ozone is the layer of 3 oxygen atoms that shields the Earth's surface from the sun's harsh rays. The stratosphere also contains very dry air that is roughly 1,000 times thinner than the air at sea level. This thin air is what makes it possible for jets to travel through the stratospheric layer of the atmosphere. The third layer is the mesosphere. This layer starts at 31 miles above the Earth's surface and ends at about 53 miles. It contains the coldest part of the atmosphere, reaching temperatures of nearly minus 130 degrees Fahrenheit. These below freezing temperatures occur in the top parts of the mesosphere called the mesopause. Not a whole lot of studies have been conducted on this layer of the atmosphere because it's so hard to get to. Jets can't travel that high, and satellites or space shuttles aren't able to stay that low. Really, all that's known is that meteors tend to burn up in the mesosphere. A meteor is a piece of rock or matter that has been broken off in space and travels through the atmosphere. When they cross the mesosphere, friction and momentum cause the meteor to burn up and appear as a light crossing the sky. The fourth atmospheric layer is the thermosphere. The thermosphere begins at around 56 miles above the Earth's surface and ends anywhere between 310 and 620 miles. This layer can house temperatures up to 4,500 degrees Fahrenheit. That's significantly hotter than the mesopause. This layer is technically part of the Earth's atmosphere, but due to its low air density, the thermosphere is usually associated with outer space. This layer is home to the International Space Station and is the layer that multiple space shuttles have flown to. Have you ever heard of the Aurora Borealis or Australis? Well, these atmospheric beauties take place in the thermosphere. Fun fact number 1, the aurora borealis and australis occur from the collision of particles and atoms in space not being able to withstand the amounts of energy they create at the point of collision. When the energy is shed from the atoms, the beautiful photons of light are dispersed, creating the auroras. Fun fact number 2, there is a layer called the ionosphere that overlaps the mesosphere, thermosphere, and the exosphere. The ionosphere gets the name from the electronically charged ions that fill its layer. The ions are created from interactions between the ionosphere gases with the sun's solar radiation. This layer of atmosphere is heavily affected by the magnetic fields from the sun and the earth. The fifth and highest layer of the Earth's atmosphere is the exosphere. This layer is the thinnest of all of the layers of the atmosphere. It merges into the interplanetary space and is composed of mostly hydrogen and helium. Its particles are spread far out from one another and aren't necessarily considered gaseous due to the incredibly low densities of the air. In this layer, there's no way for a human to breathe on their own, and even if you could, the exosphere's freezing temperatures would be enough to keep you from visiting.
Hi, and welcome to this overview of the solar system. Today we're going to take a look at what components make up our solar system and discuss the prevailing theories as to how and when our solar system came to be. Let's get started. To begin, let's clarify a couple of terms and what they mean, starting with the sun. The ball of light that you and I call the sun actually has an official name, which is Sol. The name comes from the Latin word for sun, solus. Our word solar comes directly from the name sol, so solar panels, solar eclipses, and solar flares are all related to our sun, Sol. Now let's think about the term solar system. A solar system isn't a system that's connected to any old sun in the sky. A solar system is literally the system of Sol. This means that ours is the only system in all of space that can be called a solar system. The generic term for our solar system is planetary system, and there are 3,200 other planetary systems within the Milky Way galaxy. So, what is a planetary system? To be called a planetary system, there are 3 main criteria that have to be met. First, the system contains a central body that is a star. Second, there are 1 or more planets orbiting the star. And third, the system is in a relatively flat region in space. A star is a spherical object composed of gas that contains enough heat and pressure in its core to maintain nuclear fusion. The star in a planetary system has enough gravitational force to keep all the planets inside this system. The planets orbit the star in a relatively flat plane, in elliptical paths. In order to understand the solar system and how it evolved, we have to look at its main components. By observing these bodies and their dynamics, it is possible to piece together a theory of how they began. Let's start with planets. According to the International Astronomical Union, there are 3 criteria that need to be met for something to be called a planet. First, it must have enough gravitational force to condense its mass into a spherical shape. Second, it must have a greater gravitational force than the objects close to it. And third, it must have cleared the neighborhood around its orbit. The solar system has 8 planets, but for almost 80 years, it was considered to have 9. This 9th planet was discovered in 1930 and given the name Pluto. It held its planetary status until 2006, when the IAU updated their criteria detailing what a planet is and demoted Pluto to dwarf planet status. One of the IAU's secondary criteria for being a planet is that the planet must not be a satellite or orbit any body other than a star. Pluto's largest moon, Charon, is very massive and about half as large as Pluto. This means that Pluto and Charon are both orbiting about each other as a binary system, not a planet-moon system. Pluto is also composed of solid material, which is in contrast to the four gas giants that are closest to it. Furthermore, Pluto's orbit is almost 17 degrees off the plane within which the other planets in our solar system orbit. These observations of Pluto suggest it was not originally part of the solar system. Objects formed during the creation of our solar system should have material that is differentiated according to distance from the Sun, the solid materials nearest the Sun, lighter gases farther away. They should also orbit in nearly the same plane. As viewed from above the North Pole of the Sun, all the planets in the solar system orbit the Sun in a counterclockwise motion. Almost all of the planets also rotate about their axes in the same counterclockwise fashion, as viewed from above their north poles. There are two exceptions, Uranus and Venus. The rotational axis of Uranus is tilted almost 98 degrees from the orbital plane, making it almost exactly perpendicular to its orbit about the Sun. One theory is that an Earth-sized object collided with it, shifting its axis. Venus undergoes an extremely slow retrograde rotation. A small group of astronomers now believe that Venus was originally rotating in the same direction it orbits the Sun, but somehow its axis flipped over, giving it the appearance of being in a retrograde orbit. Another hypothesis is that the planet's rotation slowed down and somehow reversed itself due to the friction of its atmosphere. Now, planets aren't the only things floating around in planetary systems. As I'm sure you're aware, some planets are accompanied by moons. A moon is simply a natural satellite that orbits a planet, dwarf planet, or asteroid. We'll talk more about asteroids later. Our solar system contains hundreds of moons, with more moons being discovered all the time. The planet with the most moons is Saturn, which is being orbited by 79 moons. Earth is the only planet in our solar system with a single moon, and Mercury and Venus are the only planets that have no moon at all. Most all of the moons orbiting planets in our solar system have a prograde orbit about their planets. This means that they are orbiting their planet in the same direction as the planet's rotation. The exception to this is Neptune's largest moon, Triton. Generally smaller than moons, asteroids are another common artifact in our solar system. Between Mars and Jupiter is an asteroid belt, which is where the majority of known asteroids orbit. The belt is estimated to contain 1 to 2 million asteroids larger than half a mile in diameter, and millions of smaller ones. Early in the solar system's formation, the gravity of newly formed Jupiter brought an end to the formation of planetary bodies in this region, which caused small planetary bodies to collide with one another and fragment into the asteroids we see today. So, how long has our solar system been around? The age of the solar system is estimated by using a number of different techniques and then comparing results. It's assumed that the solar system formed as one entity, so the Sun and planets formed around the same time. Measuring the age of rocks is one of the techniques used. The oldest rocks on Earth have been dated to be approximately 4.6 billion years old by measuring radioactive isotopes. Meteorites from the solar system have been radioactively dated to be around the same age. The oldest fossils on Earth are estimated to be about 3.5 billion years old, showing that the Earth would have been habitable for life then. Since these organisms needed light, the Sun must have formed by this time. The nebular hypothesis is the prevailing theory of how our solar system began. This theory assumes the solar system began as a large cloud of dust and gas. This giant cloud began to condense under its own gravity, spinning as it did so. Perhaps initiated by an external event, this rotational motion caused the particles of dust to acquire an angular momentum and rotational inertia. These two physical actions caused two things to happen. First, the cloud condensed so much that at its center, the mass became concentrated with enough pressure and temperature to ignite nuclear fusion reactions, creating the sun. Second, while this cloud condensed, the rest of the mass began to flatten out due to the cloud's distribution of angular momentum. Given that the cloud's mass was not uniformly dense, clumps of mass began to accumulate at various locations on the disk. This was caused by both collisions of particles and the greater gravitational forces of the larger clumps of mass. These clumps then developed into planets. The larger gas planets from Jupiter outward to Neptune are believed to have been mini planetary systems that didn't have enough mass to ignite a star in their centers. All of these Jovian planets have rings, or planes within which their satellites orbit. The nebular hypothesis is supported by several observations of our solar system. All the planets orbit the Sun in roughly the same plane. All the planets orbit the Sun in the same direction the Sun spins on its axis. Most of the planets rotate in the same direction as they orbit the Sun. Almost all of the moons of the planets orbit them in the same direction they spin. And radioactive dating of meteorites and rocks agrees with the idea that most objects in our solar system formed around the same time. These observations are consistent with the idea that the solar system flattened into a disk and that all the planets are moving in the same direction of rotation within this disk. Of course, there are still mysteries with this theory due to observations that do not support the theory. First, Venus and Uranus experience retrograde rotation. Secondly, Triton, a moon of Neptune, has a retrograde orbit. Thirdly, our discovery of many other planetary systems indicates there are giant planets, like the Jovian planets in our planetary system, orbiting very close to their star. In the last few decades, our understanding of our own planetary system has been aided by finding and studying other planetary systems throughout the cosmos. The answer to how our solar system formed is not an indisputable fact, but an ongoing inquiry. Now, before we go, let's look over a few review questions. Number 1, how many solar systems are there in the Milky Way galaxy? A, 3,200, B, 8, C, 1, or D, 80? The correct answer is C. There are 3,200 planetary systems in the Milky Way, but only one of those is called the solar system. The term solar system specifically relates the system of planets to Sol, our sun. So our planetary system is the only solar system there is. Number 2, the asteroid belt is found between which two planets? A, Mars and Jupiter, B, Earth and Neptune, C, Mars and Neptune, or D, Earth and Jupiter? The correct answer is A. The millions of asteroids that form the asteroid belt can be found between Mars and Jupiter. Number 3. Which of the following is not a part of modern theory? A. The solar system is roughly 4.6 billion years old. B. The solar system began as a large cloud of dust and gas. C. The large gas planets are believed to have been potential mini-planetary systems. Or D. The solar system formed from tidal interactions between the Sun and a low-density protostar. The correct answer is D. Choices A, B, and C are all widely held modern theories, while choice D is an outdated theory that is no longer widely accepted.
Hi, and welcome to this video about classification. Have you ever thought about the millions of organisms that exist and how they're all connected? Maybe you've thought about how a marmot and a bear might be related because they're both furry and walk on all fours. If you're thinking like this, you're thinking a lot like Carl Linnaeus, the founder of the modern taxonomy system we use to group organisms for scientific research and understanding. Linnaeus used his observations about plants and animals to sort them into taxa, or groups, so that everything was simplified and organized. Even though Linnaeus' system was morphology-based and came before we understood genetics, the framework is still in use. Furthermore, the system is always being updated as scientists learn more about genetics and discover new species. One of the more recent updates has been the addition of a domain taxon, or group, to the top of the taxonomy chart. This is the largest taxon and separates all living organisms into 3 main groups: archaea, bacteria, and eukarya. Both archaea and bacteria are prokaryotes, meaning the DNA in their cells is not membrane-bound, and eukarya are eukaryotes, meaning their DNA is contained within the cell's nuclei. Following the domain level, the classification system reads from least specific to most specific in the following order: kingdom, phylum, class, order, family, genus, and species. A mnemonic device often used to remember this order is King Philip can only find green socks. After the 3 domains we discussed, there are 6 kingdoms: eubacteria, archaea, protista, fungi, plantae, and animalia. The eubacteria kingdom consists of prokaryotic unicellular organisms, which includes most bacteria. Organisms in the archaea kingdom are also prokaryotes, and many are found in extreme environments like hydrothermal vents or hot springs. An older classification model combines eubacteria and archaea into one kingdom, Monera. The next 4 kingdoms are all eukaryotic cells with nuclei and membrane-bound organelles. Protists, such as algae, typically move by the use of cilia, flagella, or by an amoeboid mechanism. Fungi are multicellular organisms without chloroplasts and contain a fibrous substance called chitin in their cell walls. Plantae and animalia are probably more familiar to us as they include plants and animals respectively. When it comes to talking about an organism, we use the last 2 taxa, the genus and the species, to do so. The 2-name method of naming is called binomial nomenclature. For example, bald eagles are referred to as Haliaeetus leucocephalus. This is the formal, scientific way to talk about them as organisms. Haliaeetus represents their genus, and leucocephalus represents the species. Okay, so we know they're Haliaeetus leucocephalus, but what about the rest of their lineage? It is largely based on their genetic similarity to other organisms, but we also know that genetics lead to distinct morphology. Keeping morphology in mind can be a good way to not only help you memorize, but to hopefully help you understand the breakdown of how things are organized. Let's go ahead and go through the entire classification system for bald eagles together, starting at the domain and working our way down. Since they are eukaryotes, they belong to the eukarya domain. For kingdom, they are part of the animalia taxon because they are multicellular, their cells don't have a cell wall, and they ingest food instead of being an autotroph that makes its own food. For phylum, they are part of the Chordata taxon because they're vertebrates that have a spinal cord. There are many subphyla that account for other features of their build and skeleton, but for simplicity's sake, we'll keep our scope to the bigger picture. For class, they are considered to be in Aves. The order is Accipitriformes, the family is Accipitridae, and the genus is the already discussed Haliaetus. Note that the first letter of the genus is always capitalized, and the whole word is also italicized. This goes for any organism. And finally, at the species level, bald eagles are known as Haliaetus leucocephalus. Even though it seems redundant, the technical way to refer to the species of an organism is with the binomial nomenclature we talked about earlier. Just like the genus level, the species level is also italicized. We can do this for all living things like oak trees, cyanobacteria, and even your cat that's curled up next to you on the couch. Not surprisingly, house cats have a lot in common with big cats like tigers and lions. They're both kingdom Animalia, phylum Chordata, and in the class of Mammalia, order Carnivora. Finally, we have a series of Fs, Felidae for the family and Felis catus for the genus and species, respectively. So how did the house cat go from a big cat like a lion or tiger to a domesticated cat? We can actually trace this back genetically to the species that most likely preceded the house cat, to Felis libica, which is also known as the African wildcat. Domestication and selective breeding of this species have most likely caused this change. Okay, now that we've covered how organisms are classified, here are a couple of review questions to test your knowledge. Number 1. Which is the correct order of the classification system starting at the top and moving down? The correct answer is B. Remember, the mnemonic we talked about, King Philip can only find green socks. 2. What is the correct way to scientifically refer to a bald eagle using binomial nomenclature? The correct answer is D. Remember that when we use binomial nomenclature, the genus is always capitalized while the species stays lowercase, and both words are written in italics. Another perfectly acceptable way to write this would be by abbreviating the genus to the first letter of the word, followed by a period. So another correct way to write this would be H. leucocephalus. I hope this review was helpful. Thanks for watching and happy studying.